Okay, so next up we have John Seymour from ZeroFox. So put your hands together for John.
And on. And we're good. Awesome. Cool. So today I'll be talking about labeling the VirusShare dataset and indexing it so that people can actually use it for machine learning and things like that. Before I start, I just kind of want to get a feel for people here. How many people are like in the data science-y side of InfoSec, you know? Okay, and how many like reverse engineers or malware analysts or anything like that? Do we have some? Okay, cool. I would love to speak with you guys after this talk, so feel free to come on up. As was mentioned, my name is John Seymour. Here's my UMBC email because this is part of my PhD work. And my Twitter handle's here. Follow me. I'll tweet out some links after the talk. You can download some cool stuff. So who am I? Well, I'm a PhD student at the University of Maryland, Baltimore County. I'm also a data scientist at ZeroFox, and I do a lot of security machine learning work. My interests are mainly in like data sets and proving that they don't suck and can actually be used for gaining information on what we're building machine learning models on. So we'll start today by talking just basically introduction for some of you on the security side of things, like a very, very high level description of malware classification in general, what works, what doesn't. Then we'll segue into labeling the VirusShare corpus, why that's good, how it helps. Building an index, why we need an index in the first place, what that means, using a cool, sexy tool that I wanted to learn about called PySpark. And we'll end up with some pretty graphs and words of caution and some useful extensions for these things. So the main problem here is there's more malware variants created every day than we can possibly ever analyze, right? There's this thing called polymorphic malware, which basically means you run the malware and it changes its, SHA-256, hash or whatever signatures that are being used to classify these things, right? So we want to automate this process. And how do we automate it? Well, one thought is maybe we can apply machine learning to it. So what is machine learning? Well, at a high level, it's finding patterns in data, right? You have all this data, you want to find patterns in it, so you can maybe say, hey, it's likely this thing is, malicious, maybe we should check it out. Or maybe this thing is obviously, standard procedure, we don't need to look at it at all, right? And what we call these sort of patterns that we're looking at, we call them features. And we use models, which are statistical things, just to make sense of these features. And there are, of course, libraries in every programming language you want to use. I love Python. I know a lot of people like R and Weka. We just saw a talk with Weka. And here are two links that I love for just getting started on the data science side of things. Yeah. So cool. If we want to do data science, we have to have data to actually work with, right? And so where do we find data in the malware domain? Here's some of the best places that I've found for malware. I know there are lots of others, Contagio, Malshare, things like that. These are the things that I've found to be used most, in the industry and academia, things, all of them. So the first place I love is malwaretrafficanalysis.net. It's only got about 600 samples, so it's not very useful for like full-scale, productionized machine learning, right? But it's got a couple really good points to it. First, there's lots of exploit kits in it. And exploit kits were, all the rage like a year ago or something like that. And it includes the analyses for every single sample. So there's this guy who actually goes through, writes up, takes a PCAP, takes the executable, uploads it to VirusShare, tells how he reverse engineered this executable. And he actually writes it all down so you can go back and read it and learn actually how to do all this reverse engineering stuff, which is very useful when you're creating models, because you actually need a little bit of domain expertise to know like what's going on, what's 192.0.0.1 or whatever is totally fine. Don't worry about things that call out to it, things like that. So you can get a little bit of domain expertise. Then there's the Kaggle dataset. For those of you who don't know, Kaggle is a data science competition hosting site. And last year, Microsoft hosted a competition on Kaggle for classifying malware. I'll get into that in a bit. but they released about 11,000 samples of malware. They neutered them a bit, which is 500 gigabytes on your hard drive, can fit pretty well. And the task was to say, hey, here are these 9 families of malware, figure out which executables in this test set that we don't know belong to which families. And how they distributed this data was they gave hex dumps and disassembled files from IDA-Pro that they removed all the PE headers from so nobody could actually execute the files. But basically, people use standard natural language processing techniques and stuff like that in order to actually fulfill the competition. The next data set that I'd like to talk about is VX-Heaven. So VX-Heaven has about an order of magnitude more samples than Kaggle actually had. Each file in VX-Heaven is actually named with Kaspersky's antivirus label. So for example, if Kaspersky labeled it a Trojan or something like that, then it'll have Trojan and the hash and stuff like that in the file name. And it's really nice because it's really well organized, but it was last updated in 2007, which if you know malware, things have changed a little bit since XP was still alive. And yeah, so it's pretty stale. But it is the most used academic data set, so it's nice to know about. What we'll be talking about today is VirusShare. It has, I think it's increased in size actually since I made this slide, but it has about 25 million samples, which is quite a bit. It's split into chunks, and this is actually kind of important. I'll get back to this in a minute. But it's split into chunks of 65,536 samples each. So basically, chunk 0 has the first 65,536 files that this guy found. Then chunk 1 has the next 65,536 files, et cetera, et cetera, et cetera. This actually ends up being pretty useful, but we'll talk about that in a minute. All the malware is available by torrent. It's a simple password to get into. The guy is awesome. He didn't pay me anything to give this talk, but I like him a lot. And the main issue with this data set, though, is that it was unlabeled. So as the last talk talked about, ground truth is really, really important when you're doing machine learning, but it's also the most expensive part of it. It's really, really hard to do. And so what we've actually done today is label this corpus. And then I also want to shout out to VirusTotal and Maltrieve, which both have methods for collecting malware as well. There's no limit to how many pieces of malware that you can grab from them. There's a couple issues with both of those. First, VirusTotal. Generally, you need the private API in order to do useful things with it, such as download malware. And there's a lot of, A, it's really, really freaking expensive, but B, there are these licensing issues where you're not actually allowed to release raw data that you obtain from the platform. And my research is into reproducibility of ML experiments and things like that. So it'd be nice to have an open data set that we can work with that we can benchmark all our machine learning tools on and stuff like that. So VirusTotal ends up, I think, probably being the wrong way to go in terms of actually obtaining your data set. It is still really nice for their labeling and things like that. And if the licensing issues, change, obviously. And then Maltrieve as well. Basically, there's this crawler that goes around, downloads all the malware you want. But what I've found in my own research is that when people collect their own data sets in that sort of fashion, they end up overfitting pretty bad. There was a study in 2012 that actually went to Black Hat that Adobe made, and basically they said, hey, we have these 9 features, we can classify malware with them with 98% accuracy, and it turned out that it was just overfitting to Microsoft-specific coding standards, so anything that wasn't written by Microsoft ended up being labeled as malware. These are things we want to avoid, and this is how we do it. So some of the features that are commonly used in this domain, there's PE file metadata, which is basically things inside your executable that tell Windows, hey, this is how you run this executable, this is how it should actually be interpreted by the machine. And I'm not going to get too deep into it, but there are headers and sections, and people use these to grab features from. It's rich with data. And there's a very good Python library called PE file, which is excellent for actually scraping all of this from your executables. Another feature that's really commonly used in this domain are n-grams. So engrams are just, if you think about like a sliding window over text, every 2-byte sequence in the executable, you just count those up and use that as features. So for example, in deadbeef, DEAD, ADBE, and BEEF are all 2-byte engrams. And so your features would be those 3 engrams with a count of 1 each. This is actually mainly what was used during the Kaggle competition, since they had stripped all the useful information out of the files. Yeah.
Yeah? Did you make an outrageous speaker request?
I did.
Did you? What was your outrageous speaker request?
No brown M&Ms? No green M&Ms. No green
brown
M&Ms. Oh, all right, whatever. Thank you so much. All right, cool. Awesome. So some other features that are commonly used, opcodes, imports, assembly instructions, things like that. People are just trying to find data everywhere in these executables. If you'd like to learn more, there's a lot of references. Come talk to me after the talk. And then finally, some of the top performing models in this domain. Support vector machines are kind of old school at this point, but a lot of people like to use them. They're robust against overfitting in certain ways, and they're nice. There's this new thing called XGBoost, Extreme Gradient Decision Tree Boosting. It pretty much kills everything. If you know random forest or decision trees, think of XGBoost as random forest on super steroids. And then finally, deep learning is a cool hot topic that people are starting to use in this domain too. There are libraries in Python for all of these. I can't speak for Weka or R. All right. So let's talk about labeling the VirusShare corpus and what went into this. So my motivation was there's this Kaggle competition, and I'm trying to see if the models in this Kaggle competition overfit. And so what I need to do is I need to find in some disparate data set a lot more of the families that were in the Kaggle competition. So we have things like this label, Ramnet. We want to be able to find lots more examples of Ramnet somewhere else so that we can run the models that were built in the Kaggle competition on these other executables that we find. And so what we've done, well, first, we labeled this huge corpus using VirusTotal so that we can actually use it for supervised learning, things like that, but also so that we can create a search index on top of it so that we can find lots of a particular type of malware. And this could actually be useful for not only machine learning, but I think it might be useful for pen testing and reverse engineering practice as well. So that's one of the reasons why I'd like to talk to you guys after the talk. So why did I choose VirusShare instead of one of the other corpora that's out there for malware? Well, first off, obviously the size. It's huge, 27 million samples. That's several orders of magnitude bigger than the Kaggle dataset size. And furthermore, it's just the raw executables, so it's not neutered at all. It's consistently updated. As I've said, there's 20 more chunks since I actually started putting these slides together of VirusShare malware that are already up there. So we can consistently update the data set. But really, what I want to do here is make future machine learning research more reproducible, right? So I already talked about if you scrape your own, you'll probably overfit and you'll end up with one of those Titanic level disasters that was in the keynote. But VirusTotal, you can't release any raw data from the platform. And that, as a data science paper writer, that sucks for me because I normally have a methodology section in my papers, and I need to say where I got my data from. And it's really hard to actually download a data set from another academic paper or industry paper for machine learning because it's all secret sauce. This is actually really nice because since VirusShare is split into chunks, I can just say, look, I downloaded all the Ramnet executables from chunks 25, 60, and 90, and that was the data set I used for my machine learning corpus here. And so it's really easy to actually reproduce the machine learning models that other people make. And it eliminates a lot of the stochasticity that's just inherent in the machine learning process. And so if we actually start to reproduce machine learning research, we can actually figure out, hey, this machine learning model works, or this machine learning model doesn't work in this other domain that I tried, right? So we chose VirusTotal to label the executables, right? Obviously, because VirusTotal is one of the the leading vendor in the space. But also, it has an awesome API, so we can just do this programmatically. We don't need to pay lots of malware analysts to go through every single executable in the VirusShare corpus and say, hey, I think this is Vundo, or I think this is Ramnit, or I think this is Conficker, or some variant of ransomware that we don't know about, or whatever. So VirusTotal has two different types of APIs. It has a private and research API and a public API. And the difference is that the public API is rate limited, but the private research API either costs money or has these licensing agreements where you can't release raw data from the platform. And so if we labeled using the private API, then we couldn't actually distribute our results to the public and other people actually use them, right? So we ended up using the public API. And actually, this is all the code to take in a batch of executables and label it using the VirusTotal API. Okay, cool. And so this is actually what you get back, right? And so I've just formatted it prettily. This is just one line of JSON. But you basically get back each different antivirus and what that antivirus detected the executable as. So these are basically going to be the labels that we have for ground truth with working with this corpus. And so generally, antivirus labels are pretty inconsistent, but this is definitely in a step from the right direction. All right. So using the public API, it actually took 30 people and around 6 months to label the entire corpus because of rate limiting. We used a lot of undergraduates wanting extra credit from UMBC, which was nice. Also, some people from the MLSec project actually helped out and beta tested the tools and stuff like that, so that was really cool too. This is actually all the labels from chunk 0 to 233, I think. Again, there have been more since then. I'll release those after DEF CON when I actually get access to Wi-Fi again. But basically, I think it's 7 gigs compressed of just those lines that you saw earlier. And it's really easy to look at, really easy to find things. But what we want, right, is we want this tool that we can go through and say, hey, look, we want to find lots of Ramnit instances, right? And what we have right now is we have this thing that says, hey, in chunk 0 we have Win32 HFS adware .166 or whatever. We got some pups, things like that, right? What we really want is something that we can just go through and say, okay, like we have this type of label that we're looking for. How many are in each chunk? And this actually makes it a lot easier to search over this data set, right? If we want to only find malware in chunks 4, 60, and 90, what we do is we just say, hey, like, grep through it and be like, what's the count in chunks 4, 60, and 90? So this is called an inverted index. And the way you do it is basically by counting things, right? And apparently, I've heard the MapReduce framework is awesome for this. Actually, the PySpark initial tutorial is exactly this problem. So it works out pretty well, especially since I wanted to learn PySpark. And this ends up actually being the entire script, which is really, really nice. So it's like, 20 lines of code. Everything else is just formatting. And it's really easy to, learn and use. And it's actually more work to install PySpark than to actually use it, which is pretty cool. And this is what the inverted index actually looks like after we finish, right? So you can sort of see it's a CSV with the label, how many are in 000, 001, et cetera. And it ends up being really easy to use. You can just grep for Vundo. You get all the results for Vundo. This is how many in each chunk. And you can even see by inspection, look, those chunks have a lot of Vundo. If we want Vundo, we should download those chunks, right? And then this index also lets us easily explore this data. So I really quick in like 2 minutes threw up basically most frequent malware in the last recent chunks. And yeah, you can see that there's about like 1,000 of riskware, adware, screensaver, Win32, Eldorados. You can find that out in like less than 2 minutes, which is pretty nice. And you can also make a lot of pretty graphs, which is nice too. So this is one of the cool things with VirusShare is he actually posts each chunk temporally, right? So he posts chunk 0 first, chunk 1 second, chunk third, third, et cetera. So this means we can actually use the chunk number as a proxy for time, and we can see how many instances of Vundo this guy collected, in kind of over time. And so this is just a graph, again, made in like less than 2 minutes, of how many instances of Win32 Vundo this guy collected. And you can see like there's a spike there, and there's a dip here. There's a lot of assumptions about this sort of temporal plotting, right? Like, for example, A, that the chunks are sort of a good proxy for the time period, but B, that the number of instances this guy collected is actually like proportional to how many are floating around or something like that. But it's definitely like, as long as you're aware of those assumptions and things like that, it's useful. And we'll talk about maybe how to fix those things in a second. So some words of warning. First off, don't use this to compare antiviruses. So that's one thing that I definitely want to say, just to try to get VirusTotal maybe off my back for this. So they have a big disclaimer on their site, and there's a couple of reasons that I've thought of why this might be. And I think the main one is if you've ever actually submitted data back to VirusTotal saying like this is malicious or this is the file, the antiviruses choose to do that different ways. One is you can actually basically give your product to VirusTotal and say, hey, run it whenever you run into something new. But the main way that most people use is if they encounter something in the wild, they send it back to VirusTotal with the correct label. So this ends up actually meaning a lot of vendors run into sort of different sections of malware, if that makes sense. And so, for example, at a social media company, you might find links on social media that Kaspersky might not, or something like that. Another thing that you want to keep in mind when using this sort of index or data, ground truth is very, very noisy in this. First off, we've already seen that the antivirus labels are sometimes different, even though the specimens are similar, just with that Vundo index here, right? All of these are part of the Vundo family, but they get labeled, as soon as the signature for Vundo.A no longer works, then they increment it, and now Vundo.B is, a new specimen, even though it's a very similar one. But also, antivirus labels are sometimes similar, even when the specimens are different. So, like, here's an example of that, right? Here's a lot of different Trojans, and I have absolutely no idea whether those are actually similar executables or not, based on the name, right? So, like, heuristic.looks-like-Trojan is, I don't know, maybe a Trojan is basically what that label is telling you, right? So some useful extensions here. One thing is, remember that graph where we used the chunk number as a proxy for time. If we wanted to do that right, what we'd want to do is add when the specimen was first seen, rather than just how many this guy collected over time. And that's only available on the private research API, so it wouldn't be able to release to the public if we did that. So definitely, maybe find a way to do this. That might be nice. But the other major useful extension that I can see from this is some sort of stemming. So stemming and lemmatization in machine learning is basically like a way of compressing words that have similar roots together, right? So that generic.vundo.a and generic.vundo.b, we'd like them to both be called one label Vundo. But that actually ends up having some issues, especially when you have things like Trojan.abcdefg and Trojan.abcdefg h or something like that. It ends up actually being compressed on the actual incremented counter, which is kind of funny. But if we could somehow compress those labels, that might help with the antivirus labels being different, even though the specimens are similar problem. which would be really, really nice. And then finally, antivirus labeling is very inconsistent. So this would actually help us get higher granularity on our ground truth labels. So I know I blazed through that, but if there are any questions, feel free to step up to the mic.
Seeing the CVE models?
So I have not yet. That would definitely be a cool extension. I would love to do that. What?
You only have one number reference.
Yeah. But yeah, like I would definitely like to look into that too. Any other questions?
So, with the names, did you consider kind of splitting the names at the breaks and analyzing that way, since most of these are divided by either a period or a slash or something?
So
And
I
what
could
did
do
you find
that.
if you did?
Like most of the ways I've tried to split naively so far, I've run into issues where like there's all these exceptions that don't fit the mold, kind of like the malware classification problem in general. But and there's just not enough time in the day to actually go through and fix all those exceptions. So I'm actually looking for maybe some sort of statistical technique that might help.
So one of the things I've tried, and maybe you've tried and gotten better, is looking at the multiple names for the same malware and building the relationship graph between the names, and then trying to kind of get clusters of these names are all generally the same piece of malware, and there'll be overlap and things like that, but kind of try to use that to group names into a way that helps you get over the 1, 2, 3, 4, 5 problem.
Yeah, so that's actually the approach that I'm thinking I'm going to take in the next few months. I think it's probably the best way to go, but it ends up being really like expensive for me. So I'm gonna try it and see how it works out, and maybe see.
How did you handle the cases where VirusTotal labeled things as two different virus families or multiple virus families that don't share similar code bases?
Right. So right now, I release the labels with all of the different, like it's literally this this LDJSON. So you can actually like build the index even on a single antivirus or something like that. I haven't really found a good solution for that actual problem yet. Again, like antivirus labels are very, very freaking noisy. Yeah, I'm open to suggestions there, actually, is what I can say. Right now, I've built the index with all of them because my major use case is just like finding lots of Vundo malware. And so if I actually find a chunk that's not exactly the optimal chunk because two different antivirus vendors labeled it differently, it's not majorly a problem for me.
Have you considered taking the data and running it through like a relational database as well to see where other clusters might exist that don't like readily come to the surface?
Yeah, that would be a really cool idea. I'd love to do that. It's a little further in like sort of the labeling process than I intended to go, but it's sounding like I probably should. But yeah, no, actually, that's a really good idea.
And have you used something like a freak.py that does like language frequency as well on the names that it's giving back to you to see if that provides any sort of analytics?
So I have tried like counting, different labels, different like substrings within the labels and things like that. I just still get into the issue where there's all these exceptions where, like, again, Trojan.abcdefg, like abcdefg ends up being the string that occurs more frequently, like not in that exact example. But so with all these exceptions, I would have to use Amazon's mechanical Turk or something to get rid of them. But yeah.
Would you mind sharing how you did Microsoft Chicago last year? Because my team tried very hard, but we were only the 44th.
So I did not spend much time on it at all. I actually had a few friends. In fact, Gabe, were you on my team?
Yeah. So, in only the most technical sense, because like we got on it and then it became DBIR season, and like my available time went down.
Yeah, exactly. And I was like presenting my master's actual project and stuff like that. So it ended up we didn't try as hard as if it came out again, maybe. Cool. Is that all the questions? Anybody else? All right. Again, I'd like to talk to malware analysts and reverse engineers up front, or outside or something. We'll figure out a space. But thank you for having me.